You ever play a video game or watch a movie and just get lost in it? The worlds they build feel so real, so complex. It's like magic. But what if I told you it's not magic? What if I told you every single one of those stunning visuals, from a shimmering ocean to a weathered brick wall, is built from just a handful of simple, elegant rules? Well, today, we're going to peek behind the curtain and learn how to build a universe from scratch.
So that's the big question, right? How do you give birth to a digital world? It's not like you're sculpting with digital clay or painting on a screen. The answer is actually way simpler, and honestly kind of more amazing.
That's it. That's the secret. It all boils down to a few core principles of math and light. Think of it like a language. Once you learn the grammar and the vocabulary, you can write any story you want. You can build any world you can possibly imagine.
Okay, so where do we even begin? We start with the absolute bedrock of all 3D graphics, vectors. If we're building a universe, vectors are like the DNA. They're the fundamental code that describes position, direction, well, everything.
So what is a vector, really? Forget the textbook definition for a sec. Just picture an arrow floating in space. That's a vector. It's got a length, that's its magnitude, and it's pointing in a very specific direction. It's the simplest instruction you can have. Go this far in that direction. That's it. That's the basic building block.
Now, just having a bunch of arrows floating around isn't super useful on its own. We need them to interact, to talk to each other. We need to ask them questions. And that's where two really important tools come in, the dot product and the cross product. They're basically just ways of asking our vectors about their relationship to each other.
For instance, the dot product just asks a simple question. Hey, you two, how much are you pointing in the same direction? If they're perfectly aligned, you get a big number. If they're at a perfect 90-degree angle to each other, what we call orthogonal, the dot product is just 0. Super useful. The cross product is different. It's a creator. You give it two vectors and it spits out a brand new vector that's perfectly perpendicular to the first two. This is absolutely crucial for figuring out which way any given surface is facing.
All right, we've got our language vectors. We know how to make them talk to each other. Now for the fun part. Let's start actually building stuff. Let's make some shapes.
You know, one of the coolest things about computer graphics is how shapes are defined. You'd think for something like a sphere, you'd have to describe its skin, point by point. But nope. Computers use this really elegant trick called an implicit equation. It's just a simple rule. You can give it any point in 3D space, and the rule will tell you, yep, that's inside the sphere. Nope, that's outside. Or bingo, it's right on the surface. It's an incredibly clever and efficient way to define a solid object.
So when you think of 3D shapes, you probably think of spheres, cubes, things like that. But the real unsung hero of the entire 3D world, it's the humble triangle. Why? Because you can build anything out of triangles. I mean it. A character's face, a sprawling mountain range, a detailed spaceship. It's all just a collection of thousands or even millions of tiny, flat triangles all stitched together. They are the universal Lego brick.
Okay, so if everything is made of triangles, how do you talk about a specific spot inside a triangle? For that, we use something called barycentric coordinates, which sounds complicated but is actually really intuitive. Think of it like a recipe. You've got your three main ingredients, corner A, corner B, and corner C. Any point inside that triangle is just a mix of those three. If a point is really close to corner A, the recipe is like 90% A, 5% B, 5% C. This is so important for making textures and shading look smooth across the surface.
All right, so we've built a world full of shapes. It could be a simple room or an entire city. But right now, there's a huge problem. It's all completely invisible. We have a universe of ghosts floating in a black void. To bring it all to life, we need the most critical element of all. We need light. To make light work, we have to keep track of 4 key directions at all times, and they're all vectors. First, N is the normal. That's just the direction the surface is facing. Then you've got L, which is the direction pointing to the light source. V is the direction to our viewpoint, the camera or our eye. And finally, R is the reflection vector, where a light ray would go if it bounced off the surface like a perfect mirror. The entire game of computer lighting is just about the interplay between these 4 vectors.
So how do we use those vectors? Well, one of the most classic models for simulating light is called the Phong reflectance model. It's a fantastic recipe for light that breaks it down into 3 simple components that, when you add them all together, create a really believable look. These are ambient, diffuse, and specular light.
First up, you've got ambient light. This is just the general background light of the scene. It doesn't come from anywhere in particular, it's just there. Think about the soft, scattered light on a cloudy day. Its whole job is to make sure that the parts of an object in shadow aren't pitch black. It just gives everything a base coat of illumination.
Next, we add the diffuse reflection. Now this is what gives an object its core matte color. Think of a terracotta pot or a piece of chalk. How bright it is depends entirely on the angle it has with the light source. If a surface is facing the light head-on, it gets the full blast and looks bright. If it's angled away, it gets less light and looks darker. Simple as that.
And last but not least, the fun one, the specular highlight. This is the bling. It's what makes things look shiny or glossy. It's that bright little glint you see on a polished car or shiny apple. And it only appears when things line up just right, when the light bounces off the surface at the perfect angle to go straight into your eye. That's the secret to making things look polished and new.
So, we have our geometry built from triangles. We have our recipe for light with its ambient, diffuse, and specular components. Now for the grand finale, the process that takes all these ingredients and bakes them into the final image that we actually see. That process is called ray tracing.
Okay, check this out. Here's a super simple view of a scene we've built. We've got our eye on the left, which is our camera. We've got a couple of objects, a sphere and a triangle, and we've got two light sources. The fundamental problem a computer has to solve is this. For every single tiny dot, every pixel in the final image, what color should it be? Ray tracing solves this by, funnily enough, working backward.
The process itself is beautifully simple, really. First, for every pixel on your screen, the computer shoots a ray from the eye through that pixel and out into the world. Second, it figures out what, if anything, that ray hits. And third, from the spot where it hit, it casts new rays towards the lights and asks, "Can I see the light source from here?" Let's see it in action.
Here we go. Step 1, the view rays. You can see them shooting out from the eye, going through that imaginary screen and into our scene. See how that top ray goes on to hit the triangle, and the bottom one hits the sphere? The one in the middle, well, it doesn't hit anything, so that pixel will just be the background color. Okay, step 2. Let's focus on that point where our ray hit the sphere. From there, we cast a new ray, called a shadow ray, directly at the light source. We're just asking, is the path clear? But wait, look at that. The triangle is totally in the way. That means this spot on the sphere is in shadow. The computer does this for every light to figure out exactly what's lit and what's not.
Now for the really cool part. For a shiny object like our triangle, there's one more step. When our original view ray hit it, the computer casts a new, reflected ray that bounces off the surface. And look where it goes. It goes on to hit the sphere. So the final color of that pixel isn't just the triangle's color. It's a mix of the triangle's color and the color of whatever it's reflecting. In this case, the sphere. And that's it. You do this for every pixel and you get a fully rendered, photorealistic image.
So when you boil it all down, these incredible, immersive worlds are really just the result of some very clever, very elegant math. We've seen how vectors, geometry, and light all come together. It's a system of rules that lets us simulate reality, which leads to one last pretty mind-blowing question. If this mathematical language can be used to build a visual reality, what other kinds of realities could we build with it?